So welcome to this masterclass from Cambridge Leadership College. This masterclass is for students studying AS level chemistry for the Cambridge International exams. My name is Warwick. I'm one of the Z coaches at the college, and in this masterclass we're going to work on AS level chemistry paper from 2013. This is paper 2, which is the structured paper, and students have an hour and 15 minutes to complete the paper. And as usual with these masterclasses, we'll focus really on some of the things that the examiner's report pulls up, identifying areas of weaknesses that generally students are showing as they've taken this exam. Good. Okay, so first question here. The examiner pulled out that when you're completing this table, it's very important to have read the question stem before, because there's a point here where you've got to have hydrogen-containing compounds. And some of the students, the examiners noticed, didn't include compounds that were based around hydrogen. So that's, reading the question stem is very, very important. Okay, so you've got, I think this is actually quite a gentle introduction. These should be fairly straightforward to get. You're working with valence shell electron pair repulsion theory for hydrogen-containing compounds. And what you've got to remember is that you've got to work with both bond pairs and non-bonding pairs, the so-called lone pairs. Now, the first example here, where you're dealing with just bond pairs, that's very straightforward. The answer there, of course, is methane. And you've got a central carbon atom, and then around the carbon atom are these bonds, each to one hydrogen atom. And you remember that each bond is a pair of electrons. So I could draw 2 dots there to represent a pair of electrons, 2 dots there, 2 dots there, 2 dots there. Each of those bonds is a pair of electrons, and they're all BP bond pairs. And they arrange themselves in space to minimize the repulsion between them. And when they do that, they adopt this shape in 3 dimensions, which is tetrahedral. And the bond angle there in a symmetrical tetrahedral shape is 109.5 degrees. And so that shape, you have to just fill it in here, is the tetrahedral shape. Next one, you've got 3 bond pairs and 1 lone pair. Now, at that point, you're drawing, this is the ammonia molecule. All right, so, but you can see if I draw in now, these are the bond pairs. Okay, and up here, I'm just going to draw in there's a lone pair of electrons up there. Okay, and you can see they've arranged themselves in space in a very similar arrangement to what we had with the 4 carbon-hydrogen bonds around the central carbon in methane. But you have to remember that there's a stronger repulsion between a lone pair and a bond pair, so that repulsion there, than there is between a bond pair and a bond pair. And that means that these bonds are squeezed close together because of the stronger repulsion between the lone pair and the bond pair. Now, they're not asking for bond angles here, I'm just mentioning it. But you have to distinguish between this geometry of pairs of electrons, that's sometimes called the electron domain geometry, and there's 4 pairs of electrons, although one of them is a lone pair there, and they've arranged themselves in 3-dimensional space in this tetrahedral arrangement. But when you come to describing the molecular geometry, then you only have to consider the bonds that actually exist between atoms, the bond pairs. All right? So you're just looking at those 3 pairs. And you've got there actually a pyramid shape with a triangular base. So that's trigonal pyramidal is the shape here. Continuing on, next one down is we've got 2 bond pairs, okay, and for that you're going to be writing water. Now it feels a bit odd because you've done CH4, NH3, you feel like you should be writing OH2. Water traditionally is written as H2O, isn't it? And the same thing applies. So you've got the central atom, and then you've got a bond to a hydrogen atom, and then you've got another bond, that's the wedge there, another bond to a hydrogen atom, and then these other spaces in the tetrahedral distribution of electron pairs are there, just as they were for the methane molecule and the ammonia molecule. And so you've got 2 bond pairs, and let me do those in blue again. These are the bond pairs here, aren't they? And the other 2 are lone pairs. And now you've got even more repulsion between the lone pairs and the bond pairs here, because you've now got 2 lone pairs of electrons. But again, we just have to consider, when we're looking at not the electron domain geometry, which is tetrahedral, when we're looking at the molecular geometry, we're just looking at the bonds to the atoms. And so that shape, hydrogen, oxygen, hydrogen, that shape is V-shaped. Sometimes they say that's bent. I think it's easier to come up with a specific shape rather than just saying bent, to say that that's V-shaped. And you can see I've drawn a kind of inverted V there, haven't I? All right, so I think that's a fairly gentle introduction to this paper. And you're just having to distinguish here between the geometry of all the electron pairs, sometimes called the electron domain geometry, and then the geometry of the molecule, the molecular geometry, which just includes the bond pairs. And we can see that here for water, the V-shaped, and ammonia, the trigonal pyramidal shape. Okay, so now they're going to test you here with a molecule that you're not familiar with, probably. And you've got to draw dot cross diagrams. If you look up tellurium in the periodic table, then that is in group 16, isn't it? Okay, same group as water, same group as oxygen, and that'll have 6 electrons in the main shell. And so when you're bonding with fluorine, which is in group 17, that's going to have 7 electrons in the main shell. And so you're looking at a bond between a non-metal and another non-metal, so that's going to be covalent bonding. Tellurium is the central atom, and you've got to arrange the fluorine atoms around that central tellurium atom. So I'm drawing them there. And we said, didn't we, that there's 7 electrons for the fluorine atom, and then there's 6 electrons for the tellurium atom. And so that's one of the tellurium electrons there. There'll be another one there, 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 and you'll have to fill in the rest of these bond pairs and lone pairs. You can look that up in the mark scheme. And one of the critiques from the examiner was that students didn't always include all these lone pairs of electrons around the fluorine atoms. Now, the shape then is that these 6 bond pairs are going to arrange themselves in space to minimize the repulsion between them. And when you do that, you end up with tellurium as the central atom, and then you've got fluorine atom here, and you've then got fluorine atom here. I should draw that as a wedge. This is a wedge, isn't it, here? And this is the wedge going out of the plane behind the paper, and similarly here. And so These four fluorine atoms are in a kind of square, if I can draw it there, like a square, and those are called axial. Sorry, those are called equatorial. And the one above and below that square plane, they are axial. And whichever way you look at that, because these axial bonds here are perpendicular to the equatorial plane, so that angle there is a right angle, 90 degrees. And that angle there, between the fluorine there and the fluorine there, is 90 degrees as well. So whether you're looking at an axial to equatorial, or you're looking at equatorial to equatorial, then the bond angle is going to be 90 degrees. So the bond angle here, 90 degrees, and the shape, well, that's called octahedral. It's octahedral shape. Okay, still working on bond angles and shapes, molecular geometry here. Whenever you have a double bond like that, you're looking at a planar arrangement where those three atoms are all in the same plane. Now you can see once they arrange themselves in space against the same plane, then that's 360 degrees, isn't it? And so each of those angles then in the same, the 360 degrees has been divided into three. So that bond angle there is 120, as is that 120, and as is that 120 degrees. Okay, so the bond angle there for this planar arrangement of the terminal carbon and the two hydrogen atoms bonded to it, that's 120 degrees. And then you've got to say, well, you can have a reaction of chlorine with propene, and you've got to say there that the type of reaction is going to be electrophilic addition. Now, just to make sure, it's not asked in the question here, but just to make sure we understand why that is. If I draw out a displayed structure of the propene, you've got this, haven't you? And when the chlorine molecule approaches, then you get an induced dipole there. That's slightly positive because there's a large electron density associated with this carbon-carbon double bond. And that induces a dipole in the chlorine molecule here, and you end up with a slightly positive end to the chlorine molecule and a slightly negative end. And once that dipole is established, then you've got an electrostatic force of attraction between the positive dipole on the chlorine atom and the electron density in that carbon-carbon double bond. And so this is an electrophile for the electron density between the carbon-carbon double bond. And so the steps in the mechanism here is you get a bond pair of electrons moving there and a pair of electrons moving onto the chlorine there. And go back to the red color, and you end up with an intermediate where a new bond has formed to a chlorine atom. That's a carbocation, and you've got this chloride ion formed, and that has four pairs of electrons around it. And then the final step in the mechanism is that a new bond pair forms there, and you end up with the chlorine atom that we had from the first step and the chlorine atom bonded from the second step there. You can see why this is now electrophilic addition. Addition because the chlorine molecule has been added across the double bond, and electrophilic because that transient dipole, the partial positive charge on the chlorine atom, was attracted to the electron density in the carbon-carbon double bond. that dipole in the chlorine molecule meant that the chlorine molecule was acting as an electrophile for the electron density between the carbon, two carbon atoms. All right, so that's electrophilic addition, and now you've got to work out in a completely different kind of reaction if there was a substitution of chlorine into this cyclopropane here, the various possible products that you'd get. And you can see those in the mark scheme, but you end up with, I'm just going to draw in the chlorine molecules here. You could have a chlorine molecule there, a chlorine molecule there. You could have, sorry, a chlorine atom there, another chlorine atom there, another chlorine atom there. Or you could substitute, couldn't you, for both the hydrogens that are on the carbon atom there, you could substitute a chlorine atom for both the hydrogens. And so those are the three possible isomers when you have two chlorine atoms substituting for hydrogen atoms in that cyclopropane. Okay, we're now into a completely different question. We've moved on from looking at shapes and molecular geometry to questions about the chemistry of group 17, the halogens. And the way to remember this one is that anions are attracted to the anode. Okay, now this is the electrolysis of brine. Brine means a concentrated solution of sodium chloride. In a solution of sodium chloride, you're going to have sodium plus ions and chloride negative ions. The negative ion is an anion. So the anion is going to be attracted to the anode, and when it gets there, you're going to lose an electron. Okay, so that's the reaction that's happening at the anode. In water, you've got these anions, sorry, that anion and that cation there, because the sodium chloride has dissolved. But remember that water itself is partially ionized. So water itself is ionized into a hydrogen ion and a hydroxide ion. And so both of these, the sodium ion and the hydrogen ion, move towards the cathode. These are cations moving towards the cathode. And you just have to work out which one is going to be preferentially discharged at the cathode. And out of these two, the one that's preferentially discharged is the hydrogen ion. And at the cathode, it's going to gain an electron, and hydrogen gas is formed. So those are your two reactions, and you just have to remember at the cathode, the hydrogen ion, which is also present, is preferentially discharged. Okay, so now it's just saying here, well, steel is never used for the anode. Remember, this is the anode. Well, of course, chlorine gas is being made at the anode, and steel contains iron, and iron can react with the chlorine gas that's produced at the anode. So that's why you don't use steel for the anode. Okay, you can look these answers up in the mark scheme. I think there's not very much more to be said about that. That's just, there's no getting away from it. There's some hard facts that you're just going to have to learn and be able to recall under exam conditions. There's nothing really here that you can sort of work out from first principles. These are just things that you've learned during your revision and are being asked to recall on demand during the exam. Similar for this next question here, you need to know the reaction of chlorine with dilute sodium hydroxide. Now, on other occasions, I suppose you might be asked to actually give the equation. I'm writing it out here, and that's the sodium chloride that's referenced up here, and the other product is NaClO plus H2O. And then with hot concentrated sodium hydroxide, you've got a different reaction. Again, we're making sodium chloride, and this time you're making this NaClO3 plus, I'm going to write that out again, it wasn't very clear. NaClO3 plus 3H2O. So, you know, you're not being asked for those in this particular question, but it is a valid question that could be asked. So, you know, again, this is just some learning that will have to be done during your revision strategy because you're being asked to recall facts on demand in the exam. So the formula here is this one, and the formula here is that one. We'll come on to the naming of those just so you know in a moment. Now, you've got to work out the oxidation number. Well, oxidation number, you know, you can learn the rules for assigning oxidation number. There's nothing wrong with that. But the oxidation number concept is just a technique that assumes that each atom is ionic. Now, so for this example here, you've got NaClO. So that would, if you follow the oxidation number concept, you'd have the oxide ion, and because this is overall neutral, and you know that the sodium is sodium plus ion, that must mean you've got a chloride plus ion as well. Now, of course, these don't really exist, and oxidation numbers they don't have any sort of physical reality to them. They're just a way or a technique of following oxidation and reduction reactions. And so when you're working out oxidation numbers, what you're doing is you're imagining, even though they don't really exist, that each atom is existing as an ion. And when you imagine it as an ion, then the charge on it can be used to determine the oxidation number of the ion. And so you say the oxidation number of chlorine here is +1. And we write it that way round because the charges on real ions are written with the number first and the charge second. And just to show that these are not real, it's just a technique for working out and following redox reactions, you write the charge first and the number second. And that's just an indication that these numbers that you're assigning don't have any physical reality to them. It's just a technique for working something out. Okay, so that's true for, we've got the oxidation number there for chlorine. When we come here, then using the same technique, well, sodium is in compounds is always 1+. Oxygen in compounds except for peroxides is O2-. And we've got 3 of those. So you've got 3 of those. So to balance all these charges, the chlorine in there must be a +5. Now, just be very, very careful here. A chlorine +5 ion doesn't exist. We're just using this oxidation number technique to figure out what the oxidation number is of the chlorine. So the oxidation number of chlorine there is +5, and I've written the plus first, so I'm communicating that the chlorine +5 ion doesn't really exist. It doesn't exist. It's just a technique that we're using to follow redox reactions. So those are the oxidation numbers of chlorine, and you can use these oxidation numbers to give a systematic naming for these substances here, and that's called the stock nomenclature. And so to give a formal name for that, that's sodium chlorate 1. And then the stock nomenclature name for this is sodium chlorate 5. And if you're writing that out, you'd say sodium chlorate, and then you put in brackets the Roman numeral for 5. Sodium chlorate 5 for this one, sodium chlorate 1 for that one. And I didn't ask you the naming there, I'm just putting that in case you're expected to work out the name based on the oxidation number that you've worked out in a previous step using this stock nomenclature naming system. Okay, now this one here, when you study periodicity, you have to look at the periodicity as you look at all the chlorides of period 3. And you need to know that the pH, if you dissolve magnesium chloride in water, is just below 7, so 6.5 is good. And if you react silicon tetrachloride with water, then you get an acidic solution, so the pH there is somewhere in the range 0 to 3. So you've got to explain this. Well, the silicon tetrachloride is relatively easy to explain. You're just writing a reaction between the silicon tetrachloride and water, and you get that. And in that process, you produced HCl, and that is the substance responsibility. That substance is the one that's responsible for the acidic solution you got here, and that is a reaction with water. Whereas with magnesium chloride, when it dissolves in water, there's no reaction. You're looking at magnesium dissolving to form these hydrated ions. So what the examiner is looking for there is a reaction happening with silicon tetrachloride and a dissolution, a dissolving of magnesium chloride in the second step. And you have to distinguish between a reaction with water and a substance that dissolves in water. So the only kind of issue that's left hanging from this is, well, there's been no explanation for why the magnesium chloride solution has a pH which is slightly acidic. And this is just something in CIE syllabus you're expected to recall. You're not expected to give an explanation for that. We'll just cover that now so you know why that's slightly acidic. When magnesium chloride dissolves in water, you get this hydrated magnesium ion, and that actually forms a complex of 6 water molecules forming a complex with the central magnesium ion. And what can happen is that those one of those water ligands can react so that you end up with this complex. You've got 5 water ligands, and one of the water ligands has lost a proton, and the proton has now bound to the water molecule to give you this hydroxonium ion, which is responsible for the slight acidity of the solution that you recalled up here. So that's just an explanation of why the solution of magnesium chloride is slightly acidic. But as far as the CIE syllabus is concerned, you're just expected to know in recall that the solution of magnesium chloride is slightly acidic. Okay, good. We finished that question about the chlorides in group 3. We're now looking at your ability to work with calculations involving concentrations, basically. So you've got this diprotic acid. So a diprotic acid would be something like H2SO4, where there's 2 acidic hydrogens in the acid. And you're reacting that with sodium hydroxide, and you'll need 2 moles of sodium hydroxide for each mole of this diprotic acid. And when you react an acid and a base, you're going to make a salt. So you're going to replace both of those hydrogens with the sodium ion, and you're going to make a salt plus water. And you're going to make 2 moles of water. That's all balanced. And then you've got to do a little calculation here. So it's asking you for the amount. Now you should know that there's an equation that relates the concentration to the amount. The symbol for the amount is N. And so the concentration is the amount divided by volume. So if you're trying to calculate amount and you're given a volume here and a concentration here, then you've just got to rearrange this equation so that the amount is the subject of the equation. If I rearrange that, the amount is equal to the concentration times the volume. I've now got the amount as the subject of the equation, and the only thing that you have to watch is the volume is expressed in centimeters cubed, but the concentration is expressed in moles per decimeter cubed. So the units for volume aren't consistent. And the way to do that, to make them consistent, is to convert the volume here from centimeters cubed to decimeters cubed. And the way you do that is to divide by 1,000. So a centimeter cubed divided by 1,000 is a decimeter cubed. So to work out our amount, then we've got to multiply the concentration, which is 0.100, times the volume, which is 21.6, divided by 1,000 to make sure that we've got consistent units for volume. And when you do that calculation, you end up with the amount equaling to 2.16 times 10 to the minus 3, and the units for amount is mole. Now, you can see here that you've got these stoichiometric coefficients, where there's twice as much sodium hydroxide as there is acid. So if you had 2.16 times 10 to the minus 3 moles of sodium hydroxide, you'll have half of that amount for the acid. So the amount of acid, so the amount of the acid that you've got is equal to 1.08 times 10 to the minus 3 moles. And that was the amount that you had in 25 centimeters cubed. So if that's the amount that you had in 25 centimeters cubed, the amount that you had in 250 centimeters cubed, of course, is 10 times that. So that's the amount that you've got in 250 centimeters cubed. Now this last step, you've got to calculate a relative molecular mass. And just look back here. We were told in the question that 1.25 grams was originally dissolved, wasn't it? Okay, just scroll there. Okay, so down here, so we know that 1.25 grams contains that amount, which is 1.08 times 10 to the minus 2 moles. Now, we can calculate the molar mass of R. Now, molar mass is has the units of grams per mole. So to get the molar mass of R, we've got to divide the grams, or the mass, is going to be divided by the amount. And then we're going to end up, aren't we, with a unit of grams per mole, which is the correct unit for molar mass. And when you do that, you end up with a value of 115.7 grams per mole for the molar mass. But they're asking here, aren't they, for the relative molecular mass. And a relative number has no units. And the relative molecular mass is just the same numerical number as the molar mass, but without units. So the relative molecular mass is 115.7, but if you check back through the question here, at all points, you've had 3 significant figures. You can see there's 3 significant figures there. Even the concentration is expressed as 3 significant figures. That was expressed as 3 significant figures. We've had 3 significant figures all the way through, and so your answer needs to be expressed to the same number of significant figures as the smallest number of significant figures in the question. So that relative molecular mass has got to be expressed as 116. So the relative molecular mass is 116. Then you can use the data book to calculate the relative molecular mass for each of these structural formula that were given here. And when you do that, the relative molecular mass of this one is 116, this one is 134, this one is 150. And so that must mean that the unknown compound that we were calling R up here is represented by the letter S there. So because the relative molecular masses are identical. Good. So now there's a requirement to recall some of your organic chemistry. If you look at converting S into T, you can see that this double bond here has become an OH and an H has been added across the double bond. So that's we're adding, it's an addition reaction where water molecule, H2O, has been added across the double bond. So this is an example of an addition reaction. They didn't ask for it. I'm just kind of going through this as we go along. Let me try and make that a bit bigger. This is an addition reaction, and when an alkene has water added across the double bond, then the reaction is you're reacting the gaseous alkene with steam, and you're using phosphoric acid as a catalyst, and that gives you the alcohol. So that was addition reaction for the first one. Converting S into U, let's just check back. So we're now converting S into U, and you can see at this point each of the carbons at the end of this double bond, each of them has become an alcohol. So to go from an alkene to these two alcohols here is called a diol. To go from an alkene to a diol, then you need to know that you use cold acidified potassium manganate 7. And you could write that as the alkene, and you just represent the oxidation step to a diol like that. So that first reaction there was an addition reaction of water across the double bond. This is now an oxidation. I'm just writing the reaction types for you as we go along. They didn't ask for that. The next step is what was this? This is asking for converting T into we're going back this way, aren't we? So we're going from T back to S. And so to go from S to T, we had to add water. It was an addition reaction. Going back the other way, we're removing water. And so the name of that kind of reaction is dehydration. So this last one is dehydration. And the dehydration of an alcohol, where you've got an alcohol going to an alkene, that dehydration reaction, then you need aluminium oxide, and you can be heating the alcohol and passing it over aluminium oxide to dehydrate it and get the alkene. And to get the mark here, you had to have both aluminium oxide and heat. And for the mark up here, you need cold acidified potassium manganate 7. And up here, you needed steam and phosphoric acid as catalyst. So these conditions, you need to know not only the reactant, for example, we had water as steam here, but the conditions. And that you're being asked to recall both reactants and conditions to get all your points there. Okay, keeping going on with your organic chemistry. So T is this one here, isn't it? And you can see that you've got a carboxylic acid group there. Similarly, at that end of the molecule, you've got a carboxylic acid group, but in the middle, you've got this alcohol group. And you need to know that sodium metal can react with both of those functional groups. It can react with the alcohol functional group, and it can react with the carboxylic acid functional group. And when sodium reacts with an alcohol, then you get an alkoxide. And when you react sodium with a carboxylic acid, you end up with the salt of a carboxylic acid. And so the result is that you end up with this, and they're asking you to write out the structural formulae. And so you need to make sure that these substituents, that means a functional group or a side chain which is off the main side chain, is written in brackets, because these structural formula, when you write out a structural formula, it's got to be unambiguous. So if I had to draw that out, you've got, if I was drawing the displayed formula, you've got, that's the salt of the carboxylic acid, and then you've got that was the reaction with the alcohol there. And then you've got another one of these salts of the carboxylic acid over here. So the sodium has reacted both with the carboxylic acids, with both of them, and with the alcohol as well. And when you draw out or when you write the structural formula, you've got to make sure that that is the main carbon chain, and this substituent here off the main carbon chain is shown in brackets to show that that's not on the main carbon chain. Now, when you react this U, let's go back to U. So that's a dicarboxylic acid, isn't it? And it's also a diol. And you need to know that sodium carbonate is used as a test to distinguish between carboxylic acids and other functional groups, such as phenol or alcohols. And the sodium carbonate only reacts with the carboxylic acids. And so you end up with, if I just draw the displayed formula, you've got the diol, haven't you, that we saw just now. but the sodium carbonate is only going to react with the carboxylic acids. And so you've just got to show that in an unambiguous way with the structural formula, and you're going to show again, well, you've got, no, that's wrong, that's right. You've got the salt of the carboxylic acid, and you've still got that alcohol substituent there. And again, there's another alcohol substituent, and then you've got the salt of the carboxylic acid. So you're writing very clearly in the structural formula, you've got this main carbon chain here, and then for each of these functional groups, which are off the main chain, they're shown in brackets. And then finally, you've got a question about stereoisomerism. You need to remember that there's two types of stereoisomerism. There is geometrical isomerism, and there's optical isomerism. And we're just looking, let's see, we're looking at S, aren't we? Which is this one here. So because that has this carbon-carbon double bond in the middle, we're going to have examples of geometrical isomerism around that carbon-carbon double bond. You can draw those out. You can see those in the mark scheme. And then finally, you've got to take the cis isomer that you drew, and what they're saying is if you draw out that cis isomer, you can see that you've got the carboxylic acids on the same side here. So that would be, if you're using the E or Z notation, that's this is the Z isomer, and that's the carboxylic acid, and that's the carboxylic acid. And what's happening here is you're forming an acid anhydride. And to do that, a molecule of water is removed, and so you end up with this cyclic compound where you've got this new bond formed here. Yeah, and that's an acid anhydride, and you've still got this double bond here. And you know, this is now asking for the displayed formula, and the displayed formula means that you have to write down each and every atom and its bond. And you can see that I've done that here by writing out particularly the carbon to hydrogen bonds. Don't forget those. Then you've got the carbon to oxygen bonds around here, the carbon-carbon bonds. You've written out a displayed formula where you've shown all the atoms and all the bonds. Okay, so you've got these here, propane, butane. Well, that's an easy mark, isn't it? They belong to the alkane homologous series. Now, you had to write here a balanced equation for the complete combustion of an alkane. So you know that you've got C4H10, and when you go for complete combustion in oxygen, you know that you're going to be making carbon dioxide and water. And so because you've got 4 carbon atoms here, you can think 4 of them over there, and because you've got 10 hydrogen atoms here, you're going to have 5 water molecules over here. Then if you add all these up, you end up with, well, if you calculate it all, then you end up with 6.5 oxygen molecules. Now you sometimes see these combustion reactions written out like that. It's much safer to write out these balanced equations with all the stoichiometric coefficients as whole numbers. And that's what they do in the mark scheme. So to get rid of that fractional stoichiometric coefficient there, the 6.5, you're just going to multiply through by 2, so that you've got 2 lots of butane plus 13 moles of oxygen, and then you've got 8 moles of carbon dioxide and 10 moles of water. So as you need to make sure that you've got whole numbers for your stoichiometric coefficients, although the temptation is to give a fractional stoichiometric coefficient over here. Now, that was talking about, wasn't it, the complete combustion of butane? When you're using these alkanes, you may have incomplete combustion, and under conditions of limiting oxygen, then instead of completely oxidizing the carbon in the butane to carbon dioxide, it just becomes black carbon, black soot, and so the solid black deposit that you see there is carbon. And again, you've got to write the simple equation for that. You know, you're making not carbon dioxide, but carbon. You're still making water. You're going to have 4 of that. You're going to have 5 moles of water. And then, of course, if you try and balance the equation, you end up with a fractional stoichiometric coefficient in front of the oxygen. To get rid of that fractional stoichiometric coefficient, you're going to write 2 moles of butane plus 5 moles of oxygen is giving you 8 moles of carbon and 10 moles of water. And in that way, we get rid of the fractional stoichiometric coefficient and have integers, whole numbers, for the stoichiometric coefficients. Enthalpy change of combustion, you can look that up in the mark scheme, you can look that up in your revision notes. Now, at this point, they're getting you to work with the ideal gas equation. And you need to know that anytime you see this, you need to be alerted to the fact that you need to work here in SI units. Okay? And that's the typical point at which students fail with these questions, when you're substituting values in here that aren't consistent units. All right, so you've got to calculate the mass of propane. Now, there's no value of M in there at the moment, but you recall that the relationship between the amount and the mass is that the amount is the mass divided by the molar mass. And so we actually don't, we want to work out mass later on, don't we? So you can say that PV equals nRT is the same as saying PV equals the mass divided by the molar mass times RT. And because we've got to calculate the mass, we need to rearrange this so that the mass, little m, becomes the subject of the equation. So that is, the mass is going to equal the pressure times the volume times the molar mass divided by the gas constant divided by the temperature. And all we need to do now is substitute in the values to get our mass. Well, pressure here is given to us as 101 kilopascals. So the SI unit for pressure is newtons per meter squared, or pascals. This is 1,000 pascals. So our pressure value there is 101 times 10 to the 3 pascals. Our volume, you see, is 125 centimeters cubed, but the SI unit for volume is meters cubed. And to go from centimeters cubed to meters cubed, you've got to divide by 1,000,000. So that's 125 times 10 to the minus 6. So that's our pressure, our volume, and our molar mass. If you work that out, that's 44 grams per mole. You can just work that out by adding up the values from the data book. So that's our molar mass for propane. So we've got our numerator, all calculated at the top. The gas constant that we look up in the data book is 8.31, and the temperature, now again, this is set out to trap you because we're working in SI units. The SI unit of temperature is not degrees Celsius, but Kelvin. And to go from degrees Celsius to Kelvin, you have to add 273. So 273 and 20 is 293. And then if you put all those in your calculator carefully, you end up with a value for the mass of 0.2281 grams. So just a bit of care to be required when you do that, both care doing the calculation on your calculator, putting in the numbers, but also making sure that you've got correct SI units as you work through the calculation. Now, in the data book, you can look up the specific heat capacity of water, because here 200 grams of water is being raised by 13.8 degrees Celsius. And so you need to know that the heat that's being transferred is the mass of the water that's being heated times the specific heat capacity of the water times the change in temperature. Now, if you look up in the data book, the specific heat capacity of water is given in joules per Kelvin per gram. Now, we've already got 200 grams of water, so that's consistent. We looked up our units for specific heat capacity, and you can see that for units to be consistent, we should be working in Kelvin, not degrees Celsius. But 1 degree Celsius is exactly the same as 1 degree Kelvin or 1 Kelvin. So we can just, because this is a difference here, it's not an absolute temperature, we can just put in there, we've got 200 grams times 4.81 times the change in temperature, and a change in temperature of 13.8 degrees Celsius is a change in temperature of 13.8 Kelvin. And if you do that calculation, you come up with 100 and this. Sorry, I'm just reading my notes here. I can't even write. So that's 11,536.8. So that's 115. So 11,536.8. And because you've been working in joules here, the answer there is in joules. Now, it's much more typical when you've got such a large number of joules to express it as kilojoules. So that's 11,500 joules, 536 joules. So that's 11.5 kilojoules, isn't it? And so in this last step here, you've got to use the information that you had up here about the molar mass and the mass, and the information you've got here in terms of the amount of energy that was, or the heat that was transferred. So you're going to be saying that you know that 0.23 of a gram released 11.5 kilojoules of heat, but you know that the mass of 1 mole of propane is 44 grams. And so you just got to multiply up here so that 44 grams of propane will give this number of kilojoules of heat that's released. Okay, last question here, looking at the boiling points in this homologous series, methane, ethane, propane, butane. And as you go up the homologous series, then the boiling point is increasing, and you've got to give an explanation for that. And down here, there's a comparison between that straight chain isomer, butane, and this branched alkane here, 2-methylpropane. Now, all of these molecules here and here, none of them have hydrogen bonding, none of them have an electronegative atom in them to cause a dipole moment. And so the only kind of intermolecular bonding that exists between these molecules is the London forces. That's sometimes called dispersion forces. And these London forces or dispersion forces are transient induced dipole interactions. So at any one particular time, there'll be a transient dipole on one molecule, and that's inducing a dipole on an adjacent molecule, and that leads to a momentary force of attraction between the molecules. And that momentary force of attraction, these London forces or dispersion forces, are related to fluctuations in the electron density around these molecules. And as you get larger and larger and larger, you can see these molecules here are getting larger, then these larger molecules have more electrons in them, and so the fluctuation in their electron density increases. And so you're saying here that the increase in the boiling points is due to increased London forces, which in turn is a result of a greater number of electrons in these compounds here. And because there's a greater number of electrons, you're having a greater fluctuation in electron density, which is leading to these greater London or dispersion forces here. Now, when you come down to comparing this 2-methylpropane with butane, you're comparing, if this is butane, I'll just draw the skeletal formula, 1, 2, 3, 4. When butane molecules are close together, you can see that they can stack closely, like this. But this isomer here is methylpropane, so its skeletal formula is like that. And so these molecules can't stack close together. There are fewer points of contact between these molecules of 2-methylpropane and these molecules of butane here. And so the reason that the butane has a higher melting point is there's more points of contact between the closely stacked butane molecules than there are points of contact in the less closely stacked 2-methylpropane molecules. Again, you've got London or dispersion forces that are the result of, that are responsible for the intermolecular forces here, and there's just a greater chance of these temporary induced dipole-dipole interactions between these closely stacked butane molecules than there is between the less closely stacked 2-methylpropane molecules here. Very good. So that's the end of this structured paper for students of AS level chemistry. Of course, if you've got any further questions about this paper, then the Z coaches from Cambridge Leadership College will be delighted to answer any questions that you raise on the Slack channel for AS level chemistry. And so it just remains for me to wish you every success in your studies of AS level chemistry and look forward to you joining the next masterclass from Cambridge Leadership College.